The second part of the second order circuit, we have already explained how we calculate the initial conditions which are required to solve differential equation, because in the second order circuit you have to solve second order differential equation. So here this part we are talking about the source free circuit. We have source free series RLC circuit and parallel RLC circuits. So in series here we have what we call it here national response, of course, because you don't have a source, so you do not expect that you will have a constant. For example, V equal 5 plus e to the power of negative whatever. No, you do not have a constant. You will have a solution that we call it here national response that will vanish with time. So at infinity, the voltage or current here must be zero. Why? Because you don't have a source. So if you want to solve this circuit, what you need to do is just apply Kirchhoff voltage law in this circuit here. As we'll see in the next example, this is the differential equation when you apply Kirchhoff voltage law, and we usually use this alpha and omega instead of these values here, where alpha is called the damping factor or Neper frequency, and omega 0 is the resonance frequency. Omega, of course, is not frequency. It is omega equal 2 pi f, and f is a frequency. But because the relation between omega and f is just 2 pi, omega equal 2 pi times f, sometimes we call omega frequency. So omega here is called resonance frequency or underdamped natural frequency. Okay, and these are the values for alpha and omega. So let us see here how we solve this circuit, how we derive the equation. We apply Kirchhoff voltage law, so the voltage across the resistor is I times R, the voltage across the inductor is L di by dt, and the voltage across the capacitor is 1 over C integration of I dt. Okay, and of course I tau d tau whatever here, upon integration from negative infinity to t. So to get rid of the integration here, because it will be hard to solve it, so you just differentiate the whole equation. Then in this case, this will be second order differential equation. L di square by dt square, and here it will be just 1 over C it, and here R di by dt. And then you divide by L to get rid of this L. So the circuit will look like this. So we differentiate and divide by L, you will get this equation here. As I said, we replace this R and L and C by alpha and omega. So here we call this di squared by dt squared plus 2 alpha di by dt plus omega 0 square I. So in this case, if 2 alpha equals this, then alpha equal R over L over 2 or R over 2L. And omega 0 will be square root of 1 over LC. So here the solution depends on the values of alpha and omega. What you need to do is just compare alpha and omega. If alpha is more than omega, then in this case we call this overdamped. If alpha is less than omega, then it is underdamped. If alpha equal omega, we call it critically damped. And the solution look like this. So here you just need to compare alpha and omega, and you decide what's the solution. If alpha is more than omega, this is the solution for the current. If alpha equal omega, this is the solution for the current. If alpha is less than omega, this is the solution for the current. So as you see here, in all of them, you have two constants. You have A and A1 and A2. So of course you need to calculate A1 and A2. How do you find them? Using the initial conditions. And since the differential equation here is in I, then you need I of 0 and I dot of 0, or di by dt at t equals 0. That's why in the first part we talk about the initial conditions. In the first part we talk about all initial conditions, but here you just need to find I of 0 and I dot of 0. So again, if omega is more than, if alpha is more than omega, this is overdamped, and this is the solution. Okay, and S1 and S2 are calculated like this. This is the values for this S1 and this S2. If alpha equal omega, this is the solution, and of course S1 and S2 in this case is just negative alpha. So you don't need S1 and S2, this S1 and S2. For if alpha is less than omega, then in this case call it underdamped. In this case you have this omega d and alpha. Omega d is the square root of omega 0 square minus alpha square. So you just use these formulas to find the values. As you see here in overdamped and critically damped, both of them the voltage or current is increasing, and then after that decreasing to 0. But in critically damped, it will reach its maximum, and then after that decrease. And underdamped, it is oscillating like this. See, it is oscillating, but at the end it goes to 0. For example, if we have this circuit and we have R and L and C, L is 1, C is quarter, and R equal to 4 and 6. So you need to calculate I. How do you calculate I? You you need to calculate alpha and omega, okay, using the formulas. Here R is 2, 4, 6. L is just 1, C is quarter. We need to calculate alpha R over 2L. So you see R is 2 divided by 2L, so it will be 1. R is 4 divided by 2L will be 2. R is 6, 6 divided by 2 will be 3. So this is alpha. And omega will be square root of 1 over LC. So we calculate it. Here's L and C, you can calculate it. So it will be 2, 2, 2. Of course, it is not a function of R, that's why it doesn't change. Then you compare alpha with omega. Alpha is 1, omega is 2, then it is underdamped. It's very clear. This is under. Alpha is less than, so underdamped. So in this case, the solution is like this. This is the solution. Okay, where omega d equal what? Equal square root of alpha square minus omega square minus alpha square. So it will be 2 square minus 1 square under square root. This is omega d. And alpha just 1. For second part here, 2 and 2, so they are equal. So this is critically damped. This is the solution, and alpha is just 2. For the third one, alpha is 3, omega is 2, then this is overdamped. Then in this case, the solution is here, and you need to calculate this S1. S1 is what? S1 is negative, S is negative alpha plus or minus square root of alpha square minus omega 0 square. This is S1 and S2, both of them. So alpha is 3, so negative 3, plus or minus square root of what? Alpha square is 9, minus omega square is 4. So actually square root of 5. So it will be negative 3 plus or minus square root of 5, which is 2.24. You just add this one by positive and add it by negative, then this is the answer. Then you substitute by S1 equal this one and S2 equals this one. It doesn't matter which one, of course. And then after that, to calculate A1 and A2, you need to find the initial conditions and then try to calculate A1 and A2.